Do you guys know that we're switching to Brightspace D2L next fall? The Y is it's supposed to be better. The what is it's SUNY wide, so everybody's doing it. So that's the reason behind that is everybody across the city. Does it make it right? I don't know, but it is going to be. From what I saw, the Brightspace, it's better and easier to use. Blackboard, so I think a lot of it is pretty good. All right, so homework. If you need help, let me know. I'm thinking sometime we gotta have an exam here on Sharon bending moment diagram. Get that out of the way because as I started realizing this weekend, today, Sunday was Halloween, is an indication that the semester's getting short. But we really got 4 weeks this month. If you take out Thanksgiving, actually it's not even full 4 weeks. You got 3 days, 3 days, 3 days, and a week off. Back for a day in November, and then we got about a week and a half left in December. So we're really getting to the point where I need to move along. But I think what you're going to see is the sheer bending moment diagram will just keep going on and on and on. It's going to come away. So if you have problems, we can still help you. So we move on into stress and that sort of stuff. We'll talk about some weird loading that goes on and you've got a seat on. Okay, so I think that's kind of where I want to go and what we're going to be doing. Unless you guys are all panicked and not having any fun yet. And I didn't bring my notebook up. Okay. Yes? Okay. All right, so exam-wise, what's going on in your life that I need to watch out for? Anybody else? Excuse me. Anybody else planning exams? End of the week or early next week? Like seven of them all together one time. I just stuff the plan.
I think I'm probably free the first week of December.
You're free the first week in December. Ha! No. Too far out. Might as well just wait for the final exam.
Exactly, that's what I'm saying.
About the rest of you?
Ashton's is planning something, he doesn't know when he's doing it. Like Ashton's is planning a test, but he doesn't know when he's doing it.
He's planning it does, but doesn't know.
Because the last one went so well, he's just ready to give us another one.
Yeah, that almost makes sense. Unless it's a repeat of the first one.
We should do Monday before Thanksgiving. But not next Monday, the after.
Monday after. Okay, so I'm just thinking about what gets loaded into that exam.
Just this year, not even the
Yeah.
Do it right now. Okay, everybody, here's the problem. Let's do this. Eccentric loadings. Well, okay, so if it's Friday, and we did it the second hour, for an hour, and it was one question. Would that be fair?
So you're saying we take just 1 hour of 2 hours to do it?
Yeah,
Just one question.
one question, all or nothing. Well, I mean, partial grading, but I mean, really, it's not like, you know, if I give you 3 problems, you have more chances of success, but there'd still be bending moment.
What?
Friday at 11 o'clock.
This Friday?
Yeah, one question.
On Sharon Avenue.
Yep. Frank's nervous.
Oh, yeah.
But Al, how about you? Friday? Okay. Now?
This Friday?
Yeah. Yeah, now he woke up. All right, so let's try that. Now, let me see what I can create with one question. It covers generic topics that need to be covered.
Don't be ruthless.
But literally, I hate to say this is not gonna go away. I mean, once you do this, we just keep going forward. All right. Okay, so let's try that. We'll see where the world takes us. Okay, so stress and beams, all right, sigma. So we've talked about this, and I've thrown it on the board a couple times, and just worked the numbers out. But basically, we're looking at that. So this is your max moment. Okay. C is your centroid. Okay. And I is your moment of inertia. Okay. But there's also this one. Okay, section module. Okay. And if I give you a round shape, rectangular shaped beam, you really just go to MC override. Okay. If I give you something that's a W flange or a S shaped beam, it's easier to go get the stuff off the S section modules for that. Okay. So I'd like to spend a little time talking about the second part, and then we'll just practice the first part up here so you can get the hang of this. But we did centroids. This was 3 weeks ago, 4 weeks ago. Okay, I did this moments of inertia. That was at least 3 weeks ago. Okay, and this we just did. So you can go back and look all that stuff up. It's not a big deal. I know I've talked about section model just a little bit, but I think the easiest way to cover that is just go and take a look at these shapes. And here, there. Isn't it cool how the little miter board just waves at you once in a while? So anybody have a good Halloween while we're waiting for the computer to get caught up? Do anything stupid, crazy? You know what today is? You know, so let me back up. You know, there's a Boxing Day after Christmas, right? In England, Canada.
Boxing Day?
Boxing Day.
Yeah.
It's the day where the servants can go have Christmas and the lords of the manor and ladies just let them go do it. All right. So it's actually pretty cool tradition. The here in the U.S., there's nothing really after Halloween. But you know what the retail stores have that's really kind of cool? Candy's 50% off day. So you got to go buy some candy. All right, so when we get to weird shapes like this, and you can do this with almost any way you want to do this, okay? So if you get a W shape here, and I wish I could blow this, well, I can. Cool, let's do that. So let's say we got a W36 194, okay? The areas there, you might need that. Trust me, later on when we get into complex loading of beams, we'll come back to that, and yes, you're going to want that area. Okay? The dimensions are in there for the web thickness and all that sort of stuff. IX is the moment of inertia equivalent force. But then there's SX, which is a section model. Okay, so if we go to 194, it's 644, but note that it's inches cubed, not like the moment of inertia, which is inches to the fourth. Okay, because section modulus really is the relationship between C and I. Okay, so pop back here for a minute. S is equal to I over C, but if you think about it, S is in the denominator, so it has to be inverted here. So if we know something inches to the fourth divided by inches, we're going to get inches cubed, okay? So it all makes sense. So that's the relationship. Cool thing is, somebody figured out that if I already know the shape, just have it all tableized, I can make my life a lot easier. Okay? So I said what, 644? Okay. So we take the W, crap. $36,194. Okay, and if I was to do that, we take the I value. Anybody remember what that one was? 12,100. And C is going to be half of D, right? So we go down here and find the D dimension, which is 36.5. And that'll be what? 36. 18.25. Okay, so if we calculate this using I over C, what do we got? Hopefully 640, 664. But we got 663. Any decimals on that by any chance?
0.0136.
Okay. So, anybody got an explanation why there's a difference? This is less stressful part of stuff.
Just rounding differences.
Rounding differences, but 664 was based on a whole series of experiments. They actually did the test, calculated them from all different possible shapes of that side, and called that the point we use. Okay? So it allows for errors in manufacturing or differences in quality control on the beam. Okay? You're not going to be wrong if you use 664. You're not wrong if you use 663. Okay? So, one thing I'm going to remind you is, as you do things, document where you get it from. Okay? So if you're calculating it, just say so. If you're pulling it from the table, this should be reference Appendix A, Limbrunner. Okay, and you can get the page number or something else like that. If you're going to the civils, so Montana and Henry, you guys want to make sure that you refer to the AISC in English receipt, so that you get it straight, or have a valid source. Did I talk about manuals and referencing things in the past?
A little bit.
A little bit. I'll just make sure I do. When you're on the job, textbooks are not an acceptable source of references. Okay? The tables are in the back. While they'll work and get you in the ballpark, we just don't accept them as published values for the industry. Okay? Normally they do pull them from things like AICS or ASME or SAE, but it's always better to go to a source than do a secondary source like a textbook. Okay? So don't you, outside of class, don't use that in the industry. Okay? All right. So anyways, so we're good. Now, let's take a look at basically simple bending. All right, and I'm going to cheat here, and we're going to use some of the stresses from 55. No, Kips. Yeah, that's Kips. So we're going to use M over S in this case, and M is going to be 55 Kip feet divided by 664 inches to the third. Now what? Can I mix units? Frank's nodding his head. I can mix units.
Oh, wait, no, you can't. I figured you
Yeah.
mix units.
I can't mix the units. So feet's got to get converted to inches, so we can make this work. Okay. What are we actually looking for here? What's the units that we're going to look for on stress? Anybody remember from when we did axial stresses? Feet per inches squared. Okay. So we're looking for, or pounds per inches squared. We're looking for that. All right. So to do that, we're going to have to do what? Make sure we multiply 55 Kip feet times 12, come up with our answer. Okay? I'm pointing this out because, believe it or not, that's a simple place that mistakes get made. And if you make it, you won't be the first, nor will you really be the last. Okay? Anyway, so what do we got for a stress there? .994.
Units are
Yes,
they, or did we convert the KIPS? So really, we are 994 pounds per inch squared. Okay.
So watch that, when you see KIPS, this is me personally, okay?
But if I see KIPS, I'm going to take that immediately to 55 times 10 to the third pound feet, and then do the rest of it. Okay? You're going to have to make a choice someplace.
And it's okay if you choose to do it at the end, just remember to do it at the end and don't skip it over. Is that fair? Better? Now, the interesting thing is, you two, not to make you weird, but your industry chooses to call that KSI, okay?
So if I was to leave this in terms of the answer you gave me here, it would be called 0994 KSI instead of PSI. Okay?
So that's legit, you can get away with that. All right? Now, the other thing, I want to think about the stress for a minute. What was the width of that beam, or that depth of it, the whole, the D value? 36.5 inches, right? It's that tall off the floor, okay? And I put 55,000 pounds per foot as the maximum bending moment, okay? And all I got was literally 994 PSI, okay? So it was really huge, right? So it wasn't gonna deflect much, it wasn't gonna have much of a load on it, and we're probably safe. Okay. Let's go play with a different one here, just so you can get the scenario out of it. Stay in the S shapes that we had.
Well, let's talk a little more about the table here. So all the numbers start large at the top and go small towards the bottom, okay? And we picked a 36. Let's go down and pick a 8 by 13, okay? And of course, in the bloody world of things, S is this column here. So 9.91. So for a W 8 by 13, S, what did I say it was? 9.91?
Yeah.
Okay. So the same 55. What do we got for an answer there?
And I guess before you get done calculating, do you expect that the stress is gonna go up or down? Down? Stress gonna go up? We'll change the S or go down? Oh, right. What did you get first?
66,599.
66,599. Okay, so we went from 994, 66,599. Okay. Cool. All right. Now, it's not part of strength of materials, but it is part of material selection one. Okay. So if I tell you that the beam for 813 and the 36 by whatever it was is 836 steel. Okay. So it's a grade of steel that is stands for 36,000 pounds per square inch of yield. Okay. On the first beam, did we yield? $36,000. So let me write it down so you can see it. Okay, so that's our yield strength. So on our first beam, which was a 36,194, okay, so the question is, if that's my yield strength for the material, did this one fail and did this one fail? Which one broke?
$994.
The 994 broke? The other one broke? Okay, now we got difference in opinion. Okay. What's the stress mean to you? You thought about this yet? How much force it's going to take to expand it. But it's the force over the area, in this case it's the bending. So, did it bend? Yes. Did the first? Well, let's do this. Let's call this one A, and we'll call this one B. Did beam A bend? Yes, but by a lot or just a little, just a hair, okay? Matter of fact, you probably wouldn't even notice it that it bent, okay? Did B bend? Did B bend past the point of yield? Yes. By roughly how much? At least double, okay? So somewhere in there that sucker went, and probably if we look up the ultimate stress of 836, it may have even failed, okay? Make sense, Muhammad?
Yeah.
Okay. Now, here's one of the other things you can always get asked for this. So if we take a look at A, our factor of safety so we have 36,000 divided by 994. Okay, what's that number come out as?
$36.21.
Okay, and now B, if you do the same thing, same equation,
you got, Frank?
0.54.
0.54. Okay. Which one do we want to choose? A, right? Because B would be Muhammad hanging on a rope that's only half his weight, or capable of holding half his weight. He's now in the alligator. Right? So that'd be a bad thing to do. But 36.21, do we really need to be that safe? No. Okay? So we talked about factor of safety back in the beginning of the semester, and now that we're doing pending, it's time to bring that back into perspective. So depending on your application, you're looking for something that's probably going to be 1.5 to 2, maybe 3. The only place the factor of safety gets really tight to 1 is the airline industry. And when they're designing airplanes, factor of safety on most wings is like 1.2, 1.5 tops. Montana's I just went like this big, and does that scare the hell out of you?
Yeah, why like alcohol? That is just
It's weight ratio. Okay. The good news is the material they use to build airplanes out of isn't like in World War II where they're just taking metal off the production line and trying to make it fly. They're using titanium and stuff that's got a really high strength to it. So getting that close and knowing that it's okay. But if you ever sit in an airplane on a wing and you watch the wing do this in flight, make you nervous? Well, most passenger, yes. But as an engineer, I sit there and go, cool, look at the harmonic going on, and try to figure out what the stress levels are. It's doing 550 miles per hour and density, yeah, you can get all kinds of stupid things. So, trick is, you check your factor of safety because you're going to go pick a material that would be someplace around 2 or whatever your design intent was, okay? So keep that in mind because I could always tell you, design this beam, see if a factor of safety of 2 and whatever material it is or size and shape you pick from, that'll make a difference in your world, okay? The other part of this is 36-inch beam. That's a really big piece of steel, okay? And if it's going 12 feet, I don't really need 36 inches of height, okay? If it's a bridge where I'm going to span 100 feet, I probably do want that, okay? Later in the semester, we'll get into deflection and we want to know how stiff it is and that sort of stuff. But you may need to be that thick. But you're also working within some parameters of what you can fit into the project, okay? Now, in the world of mechanical, something 36 inches high that I'm using a W shape for, it better be a girder that was designed to carry an overhead winch to pick something off the floor to move it to another location. Well, the only time I'm going to get that big, okay? Civils, unfortunately, you guys are going to play with those things that big all the time because you're spanning big distance. Most buildings, though, don't have 36-inch pieces, but bridges do, okay? All right, what else am I going here? What do we got? Okay, so we're good there. Okay, now let's talk about combined loading. So what if I got a beam that looks something like this? And I'll put a roller on that end, make this end fixed. What's that look like? We haven't talked about translational forces yet, what we're about to. Okay? So this is a section where things get a little complicated, but it's not that horrible, okay? We do need some dimensions on here, so I'm gonna make some up. Let's make it,
6 feet, 6 feet, so we're 12 feet overall. Okay, and let's make the distance from here to there, we'll do 2 feet. Could just be an inches too, but we're going to do 2 feet, okay?
what's the shear diagram look like for this thing? Frank, you ever seen anything like this last year? No?
So what's this goofy little, put this in red, this force doing on this piece of steel out here hanging over the top? Okay. So we got 50 kips, we got 2 feet to the center line. So what happens just to make that little section of that beam balance out? What is it? What is it? So back to statics here, folks. What makes this become neutral? Okay, Montana, put 50 kips on that end of that. No. Now what's happened? I got a reaction, right? What's my reaction? 50 kips times 2 feet, right? I got a moment that has to counteract that out there, right? Okay, cool? Okay. So kind of the same stuff we've been doing, but now I just threw a little twist in here. So we got a moment there, and that moment will be 50 kips times 2 feet, or 100 kip feet, okay? So that's going to play in when we do the moment diagram. But now we still got to deal with that force. Where's the force act through? This is the tricky part about translation. So where's that 50 kips want to act through the beam? No, because that's where our moment's going to be.
But Montana shook his head yes, so it has to be.
Do what?
I saw him shake his head yes, so it has to be.
Montana shook his head yes?
The shaking. Oh, never mind.
He just, I
Yeah.
think he's nervous. You're stressed out, he's nervous. So that actually gets translated down to the beam.
Like it's just straight down.
Straight down. Okay? It is the force that's driving down there. So it actually acts at 8 feet from the left, okay? And that's why it's called translation. Okay? So the shear diagram is gonna be a little bit weirder looking, and then the moment diagram is gonna have a nice little extra bit of kick because of that moment, okay? And that causes some really lovely things to happen to your calculations. Alright? But it's how you wind up dealing with these things. So, that's a pretty cool little introduction. We'll work through these on Wednesday. Right? Yeah. And we'll have some fun with them. Okay? But do people do stupid things and load beams this way? There's people welding things on beams all the time and never pay attention to what the impact is. So, kind of what we're looking at. All right. See you on Wednesday, folks.
Don't forget, today's COVID testing day. Go get your COVID test.